This is the fall 2023 exam that was given. Here's problem number one. You're given that f of x is equal to 6 over x minus 3. G of x is equal to 12x minus 3. And you're actually given a third function, which we no longer use. So that's not going to be something that we're going to pay much attention to in this lesson, because that question is no longer on the final exam. All right, so here we go. So this was 10 points back then, but it's really an 8-point question. So again, we want the domain of f of x. Which means we want to take the denominator. So here's f of x. So this fraction is undefined when the denominator is equal to 0. Otherwise, it's defined for every other value. So what we don't want is for x minus 3 to equal 0. So this is how we set it up. We say x minus 3 is not equal to 0, and therefore x is not equal to 3. So in other words, negative infinity to 3, and then from 3 to infinity. This is the domain of the function. Question B, find the domain of g of x. Well, g of x is equal to 12x minus 3. Therefore, we come to the conclusion for any linear equation, the answer will be all real numbers. This is one way of writing it. I'm not sure I ever mentioned it, but this symbol means all real numbers. But another way of saying all real numbers, of course, is to say negative infinity to infinity. Question C. Find f of g of x. Find f of g of x, which means we want f of g of x. And so if f of x is equal to 6 over x minus 3, then we want f of 12 minus 3, which would be 6 divided by 12 minus 3 minus 3. 12x. And that would be equal to 6 divided by 12x minus 6. And we could do some simplification here by factoring a 6 out of the denominator, 2x minus 1, and then cancel out numerator and denominator, and we wind up with 1 over 2x minus 1. So in other words, f of g of x is equal to 1 over 2x minus 1. And then problem D will be to find the domain of f, the domain of f of g of x. So once again, when the denominator has to not be equal to 0. So therefore, 2x is not equal to 1, and x is not equal to a half. So once again, negative infinity to a half, and from a half out to infinity. And that would be the domain for that. And that's the end of the problem. I know that there's another part to it, but that question is no longer given. So we're not gonna be referring to that problem at all. Let's go right on to question number 2. Unless there's a question. If there's a question, stop me. Otherwise, I'm just gonna roll on through. Okay, question number 2. Question number 2 is you're given f of x is equal to x squared minus 4x plus 5. And you're asked to find the difference quotient, f of 2 plus h minus f of 2 divided by h. And of course, once again, it was left out that h cannot equal 0. So, what we want to do is find f of 2 plus h in this function. So f of 2 plus h is equal to 2 plus h squared minus 4 times 2 plus h plus 5. I'm just again checking my work. Did the substitution correctly? Okay. And this becomes 4 plus 4h plus h squared minus 8 minus 4h plus 5. Let me draw a line there so we don't interrupt those two. And now let's put the h squared at the beginning and then get rid of it. Positive 4h, negative 4h. Very interesting, huh? Negative, that just is 0. And then we have 4 minus 8 is negative 4, positive 5 is positive 1. That's it. That's the whole thing. So in other words, f of 2 plus h is equal to h squared plus 1. Let me just check that. That looks so weird. Yes, that's it. That's what I have here. Okay, and now we want f of 2. So f of 2 equals 2 squared minus 4 times 2 plus 5 equals 4 minus 8 plus 5 equals 1, which is exactly what our check is. When this equals that, then that means that we're doing this correctly. Okay, now we go back to the original difference quotient, and we have h squared plus 1 minus 1 over h. This drops out. We get h squared over h, which equals h. So the answer is just h. Let's do problem number 4, because I have room here to do problem number 4. And then we could go back and do problem number 3. So we're doing problem number 4, which is the log to the base 9 of x minus 5 plus the log to the base 9 of x plus 3 is equal to 1. So this is a logarithmic expansion which we would like to compress. And the log of the log of a sum, not the log of a sum, but the sum of the logs comes back to the log of a product. So the log to the base 9 of x minus 5 times x plus 3 is equal to 1. And then we want to convert this to exponential form. So x minus 5 times x plus 3 is equal to 9 to the first power, which is equal to 9. You know, I guess we'll leave it like that. And then we get x squared minus 2x minus 15 is equal to 9. Bring over the 9. X squared minus 2x minus 24 equals 0. Minus and plus x equals -4 and x equals 6. The -4 is the extraneous root because you cannot, well, let's go back here. If we put in a -4 here, that's -4 minus -5 is -8, -9. You cannot have the log of a negative number. So therefore, this is the extraneous solution. It's usually the negative value. This is extraneous, and the answer is x minus 6. Problem number 3, the graph. The graph question. Given that g of x is equal to -4 cosine x over 2 minus 1. Okay, and obviously you want to determine the amplitude. Now, since this was the department test, they don't believe in talking about, oh, wait a minute. Yeah, they don't believe in using the frequency. So on my test, it's going to ask you for all the things that I've been focusing on, which is the amplitude. So let's just, go through all of them. The amplitude, which is 4, not -4. It's the absolute value of the number that's there. So it's the absolute value of -4 is 4. The frequency, which the department doesn't think very highly of, apparently, but I like it. So the frequency is actually 1/2, which means that over the course of 0 to 360, you're going to have 1/2 of the cos. Let's do a parent function, because then we could talk. We don't have to talk in abstractions. So this is 0. This is 360. And this is 270. And 180. And right down here oh no, that's it. I guess that's it. Oh, no, excuse me. Yeah, I'm sorry, my apologies. This is 90. I thought I figured I left something out. This is 180 right here. Okay, so that's what it looks like. And so half of the graph is what we're concerned with. The half of the graph will be right here. So when we actually decide to graph this thing between 0 and 360, it's going to occupy from here down to here. That's half of the graph. And the period, which is how long it will take to make a full cycle, will be 360 divided by a half, which is 720. So when we actually wind up graphing the entire period, it's going to go all the way out to 720. And I think this question will ask us for 2 full periods. So once again, as yesterday's problem was, we're going to actually go out to 1,440 degrees, which is 2 periods. Let's continue. The midline. Possibly the most important part of the whole problem. Y is equal to -1. Also, what they don't have is the domain, probably because it's always going to be negative infinity to infinity. The range, which is, you could either do that now, it's going to be the midline plus the amplitude. So -1 plus 4 is 3. And -1 minus 4 is -5. Well, you could actually, I think I've been stressing, well, let me just write it below it. I've been stressing that you put the negative first and then you put the positive. So starting with negative, but let's graph it and see what happens. So let's give ourselves plenty of room to do this. All right, so this is the first part of the problem. It's on the exam we just had, it was worth a lot of points. So it's a lot of points that's right here alone. And now we graph it. So here's the graph. And we're going out very far, remember. Okay, so this is y equals -1. I think y equals -1 yesterday also, I think. So -1, and then 0, and then 1, and then 2, and then 3. So from -1, we count up 4. 1, 2, 3, 4, and that will be the upper part of it. And then from -1 going down 4, we go to -2, -3, -4, and -5. So that's, from -1, we go 1, 2, 3, 4. And that will be the bottom part of that. And then the graph will look like this: 90, 180, 270, and 360. And then, of course, it'll go out to 720. And then even it'll go out to 1440. That's 2 periods. Okay, so this is going to be where where the graph is going to take place. So it's going to start at the highest point, which is 3, and it's going to go through 180, I imagine, and wind up there. So that's what the frequency tells us, that half of the normal graph, the normal parent function, is going to wind up from 0, x equals 0, to x equals 360. And then the full period will actually be coming up like this and wind up over there. Okay, so that's one full period. And then the same thing will happen here. And as I said yesterday, the midpoint, I think, is 1080. So this will come like this, and then up again, and wind up over there. And that's what the graph will look like. Oh, I made a tremendous mistake. What did I do wrong?
You're
It
supposed
be
to, it's the
reflected.
yeah,
Right?
right.
There it is. There it is. So this is a very nice graph. This is one of the nicest graphs I've ever done, right? But it happens to be totally wrong. And it's not totally wrong. It's just right side up, and it should be upside down. So let's leave it the way it is and just put the right one starting at the bottom, going up to there. And then, well, now it's getting confusing to look at the two at the same time. So I'm going to have to do another graph. But I think I'll do the other graph right below it rather than erase this totally, okay? So let me pull up a chair here because my back has been hurting me in the past. So let's do another graph. I made a mistake. Don't mind saying it, don't mind saying it. Y equals -1, and then here we go to 0, to 1, to 2, to 3, and then -2, -3, -4, -5. And this will be 90, 180, 270, 360, and up to 720. That's one whole period. And then we'll do the other one as we move along. Okay, so in other words, this is what we're graphing. But it's upside down, so we start here. And I like to do these things over here to show what the parameters are. So it starts here and goes like that, and then like that. And that's the entire period. This is not a good graph, because it's supposed to, from 0 to 360. This is not a good graph. This is not my day for graphs. I've always had trouble with the cosine graph. So it goes actually from 0. So this is what it looks like. Right? That's from 0 to 360. So that's this, except upside down. And then it's going to go like this and end up over here, over there. So it's the mirror image of what we have here, but it looks like this. Okay, and that's one full period. And then it's going to do the same thing from 720 to 1440. So it's going to go like this and go like that and then wind up like that. Okay? So that's what the graph looks like. So, that's what that's the difference between the two graphs. This graph is the mirror image of this one. It's just, this is flipped over. The max becomes the min, the minimum. Wherever you see a maximum, that's where the minimum is on this, on this graph. And the opposite is true as well. Okay, so the only thing we have to do now is to graph 5 key points. And as I've said, and was indicated on the last test, the class really gave their own key points. To me, a key point would be 0 for X and -5 for Y. That's the starting point. And then 180. And that would be -1. And then 360. Well, actually, what would be the next? Yeah, let's do 360. 360 is the maximum, which is 3. And then we can do 720. Doesn't matter. You could choose any points you want. 720, it's again -5. And then at 1440, which is 2 full periods, it goes down to -5 again. I mean, you can choose any points you want. Any points you want that makes sense is an acceptable answer. So they don't clarify what exactly a key point is, and you could do any points you want. And that's the entire problem from beginning to end. So it's a big problem, very big problem. But this is what you have to look out for. And I seem to have some difficulty with this, obviously. That negative up there, can you see that? This negative up here is very important. So, before you start graphing,
you should look at that negative and say, well, I'm not doing a regular graph. I'm doing the reflection of a regular graph, which would be the actual graph, but reflected on the x-axis, well, not the x-axis. In this case, it's on the midline. We should say that it's reflected on the midline, which is what we did here. It's not the x-axis, because the x-axis is a different, different line, but it's reflected on the midline y equals -1. And you can see how that works from here. Although my graph here is a beautiful graph, I think. The graph here is not so beautiful. Like it should be more, it should be more accurate within itself. And then, of course, the 5 key points, and that's it. Anybody have anything to say? Okay, so we're moving on. Unless somebody has something to say, we will move on. So let's go down here. And let's move on. We did question 4 already, so we could go to question 5. So question 5 gives you a function. And the way, and they ask for the domain and they ask for a bunch of stuff, but I like to do this problem my own way. So I would like to do this problem, as I said yesterday, by factoring the denominator. And we know that if there's an x plus 2 on top, we know that there'll be an x plus 2 here. That's just, very, very obvious from the construction of the problem. And that'll be x minus 4. So let's see, the -8, yes, and -2. Okay, good. All righty, so g of x is equal to x plus 2 over x. I wanted to leave that before I started crossing things off, but the next step is to do this, and that would give us g of x equals 1 over x minus 4. This is important because this is what we're going to use to do the graph. So we need to know a couple of things first, though. We need to know the horizontal asymptote, which is always y equals 0. It's always y equals 0. The vertical asymptote, in this case, x equals 4. In other words, taking the denominator and setting it equal to 0. So x is equal to 4. Okay, so that's so far all we will. So let's just do that. Let's start with that. So here's the y-axis. There's the x-axis. And x equals 4 is over there. Right, so we're going to put one graph in here like this, and the other graph in here like that. Actually, you should have done something I didn't do, and that is you should have graphed the parent function, just to give you an idea as to what it looks like. So this is kind of, it doesn't ask for the, I don't think it asks for the parent function. It doesn't, but that's important, because that gives you an idea as to what the graph will look like under perfect circumstances. A vertical asymptote of y equals 0, of x equals 0, and a horizontal asymptote of y equals 0. But we move it over because the vertical asymptote is x is equal to 4, even though the horizontal is y is equal to 0. Okay, now the only thing we need to know is if there are any holes or discontinuities, and yes, there are, because we've gotten rid of the x plus 2's, and we just used the x minus 4, but this function is also not going to be defined when x is equal to -2. because x plus 2 is equal to 0. Therefore, x plus 2 equals 0, x equals -2. So when x is -2, let's say right about over here, and when you're using, an eraser, if you're using an eraser, I would suggest you do that. It looks nicer. So there it is right there. X is equal to -2. Then you use the easy one down here to find out the value of y. 1 over -2 minus 4 is -6. 1 over -6. So -1/6 would be the discontinuity. Now, as far as I'm concerned, that's the end of the problem. But they actually say, find, the domain. We need to know the domain. So the domain and the range, as a matter of fact. So the domain will go from -infinity to the whole, or the discontinuity of -2, and then from -2 to the vertical asymptote, and then from the vertical asymptote out to infinity. So that's an important part of the problem, obviously, that I just forgot about. The range will go from -infinity to -1/6. And then from -1/6 to to y equals 0, and then from y equals 0 again out to infinity. So this is -infinity, and this is +infinity. All right, so these are important. Does it ask for that in the problem? Sketch the graph, find the domain. Yeah. Let me see if I have it the way I have it in my notes here. Oh, they just ask you for the domain. They don't ask you for the range. But that's the range. That's the whole problem from beginning to end. And you could say that there is a whole. You could say the whole or the discontinuity, a more elegant way of discontinuity, a more elegant way of putting it, the discontinuity is the point -2 when x equals -2 to -1/6. And that's the complete problem. You've stated everything that you need to state now in terms of this function. So let's review it. So you get the function, you factor the denominator. It will always have this characteristic of the fact that you could cancel out the x plus 2, something like that will always occur, leaving you with a very simple function to graph, which we then did over here by first indicating the horizontal asymptote was y equals 0. The vertical asymptote was x equals 4. So you put that in there. But then you go back to the original function and you say, well, but I haven't dealt with x plus 2 over here. So let's figure out what the whole will be. This is the asymptote, but this is the whole, x equals -2. And there it is right there. That's the value of x. This is the value of y by substituting x by substituting -2 for x. And that's what it looks like. And, they indicate, are there any holes or discontinuities? The answer would be yes right here. And then the domain, and this particular test did not ask for a range. So that would be the end of the problem. That's the whole problem. Okay, so problem number 6. A partial fraction. So this is what the question says. Find the partial fraction
decomposition. Oh, and you're given the following function. X minus 47 divided by x squared minus 4x minus 21. Okay, so partial fraction, and we're decomposing this. So in other words, x minus 47 divided by x squared minus 4x minus 21. The first thing you do always is to factor the denominator, which will always be factorable. So you never have to worry about it not being factorable, negative and positive. Okay, so negative 21. And when you add them, you get negative 4x. So that's that. And this will equal a over x plus 3 plus b over x minus 7. Okay, but the part of the problem, so in other words, we took the fraction, we factored the denominator, and we put a number over one of the denominators and the second number over the other factor in the denominator. All right, so in other words, what we're looking at now is the x minus 47 over x plus 3, x minus 7 equals a over x plus 3 plus b over x minus 7. And we want to solve this fractional equation for a and b. All right, so let's multiply by the least common multiple, which is x plus 3 times x minus 7, x plus 3 times x minus 7, and here x plus 3 times x minus 7. Okay, so that's what we have. This drops out with this drops out with that. You get x minus 47 equals, this drops out with that, a times x minus 7 plus b, that drops out, times x plus 3. Okay, so with all that, this is the most important thing right here. We've gotten down to something we could actually solve. If you want to get rid of if you want to get rid of the a, so we could solve for b, you have to make this equal to 0. So we need x is equal to 7. And substitute it into the entire equation. Okay, and you could see that 7 minus 7 is equal to 0. So that whole term will drop out. This becomes negative 40 equals 10b. Divide by 10, and b is equal to negative 4. Then we want to get rid of the b, so we could solve for a. So therefore, we have to let x equal negative 3. So when x is equal to negative 3, this will become -3 minus 47 equals A times -3 minus 7 plus B times -3 plus 3. And this becomes -50 equals -10A, and that drops out. And when you divide by -10, A is equal to 5. Hard to believe that the people who created this problem, I think they actually gave it 5 points. Imagine that.
Which I change. I don't, I change the point values because I don't like, I think this problem is worth much more than that. Okay, so we're going back up to the top then to the point to to write the answer. X minus 47 over x squared minus 4x minus 21 equals 5 over x plus 3. And the b is negative, so I'm making that -4 over x minus 7. This is the answer. Remember when we were doing this, however, I said that here's a check, and the check is to cross multiply and see if after we cross multiply, we get that numerator. So let's do that. Let's do 5x minus 35. Well, that's tricky because there's a negative over there. Well, we'll use the negative for the 4. So 5x minus 35, and then -4x minus 12. And that comes out to x minus 47. So you see that is your check. If this equals this, then we've done the problem correctly. Problem number 7. Okay, so in the first part of the problem, that's problem A, we have 5 times 2 to the -4x plus 3 is equal to 160. Now, well, the way I like to solve equations when I remember is to always write the equation over again. So I always have the original. And the first thing you would do is divide by 5. And you get 2 to the -4x plus 3 is equal to 32. Now, if this is a 2 and this is a 32, you know that this number will be, you could express this number as a power of 2. So you know that it's going to come out that 32 is equal to 2 to the something, which it happens to be to the 5th. If the bases are the same, then set the exponents equal to each other, which I just did there, and then solve for x. So you get -4x is equal to 2, divide by -4, and x is equal to -1/2. That's the answer to that part of question 7. These are all standard. They're all going to come looking like this. And you divide by this number. That number will always be a fact of a power of this number. So you know that this can be expressed as 2 to the something. So you just try a few things, 2 to the 3rd. If you're not familiar with it, try all the different powers. And it eventually will come down to this, and that's the end of the problem. Okay, so that's part A. Here's part B. Part B is the natural log of x
minus 4 is equal to 8. So once again, this is the same thing as this. The base is E. And from here, we go e to the 8th is equal to x minus 4. And let's turn it around so that the variable is on the left. You know I prefer that. After all this time, you should know that. E to the 8th. And then we should bring the 4 over. And whatever x is equal to, it's equal to e to the 8th plus 4. Okay, so now the only way to solve this is to use a calculator, which, okay, hidden over here. Okay, so what you do, if you remember from yesterday, is you do second function ln, which gives you e to the some power, which is going to be 8, and then plus 4, and the answer will be 2984.95. 20, let me see if I have that here. 2984 point, actually 0.96 if you round it off. So the answer will be, I mean, it comes out to 2,284.95789 on the calculator, which, you know, you can round that off to 2,984.96. That's an acceptable answer to that question. And even that's not an accurate answer, but you know, we can't go on forever with this, so you put it to that. Okay. Now, the question that I have, and I, you know, if nobody doesn't understand it, that's fine with me. But does everybody understand how to use the calculator to figure out this part of the problem right here? I mean, you know, you could go from here to here and, you know, study it and understand how to do it, but, you know, the calc, you have to be able to use your calculator. There's no way this could be done without a calculator. That's question number 7, and we go to question number 8. Clean up a little bit here. Question number 8. All right, so we're given, this is a nice straightforward problem. Given that the sine of theta is -2/3, sketch the angle in standard position, find cosine theta and also tangent theta. And the all important information is that theta terminates in the 4th quadrant. Okay. So, you know, drawing the angle in standard form just means that, you know, you're taking this information and you're drawing a terminal line in the 4th quadrant. That's all that means. So, you know, you're going like this, and you're saying, well, here's the angle. Here's the angle, theta. Okay? So, you know, and it all makes sense, because if it terminates in the 4th quadrant,
Sine is definitely negative in the fourth quadrant. Cosine is positive in the fourth quadrant. And tangent is negative in the fourth quadrant. All right, so keep all that in mind. So before we actually even do the problem, you're just, kind of laying out all the pieces of information that are very important for us to know. Drawing the angle as it terminates in the fourth quadrant, which it tells us in the problem, and therefore cosine will be positive, tangent will be negative because tangent is positive only in the third quadrant. Sine is indicated as negative, which we know is true. And now we're ready to use the Pythagorean theorem. And the sine of theta is 2/3, and that's opposite over hypotenuse. And you want to find the missing side because you'll need that for both cosine and tangent. Okay, so we're using the Pythagorean theorem, x squared plus 2 squared is equal to 3 squared. X squared plus 4 is equal to 9. X squared is equal to 5. And x is equal to the square root of 5. So this missing side is the square root of 5. And I'm just making sure I have everything correct. Very easy to make a mistake when the problem seems pretty easy. Okay, well, that's all taken care of. Now, cosine. Now we're answering the two questions. Cosine of theta is going to be positive the square root of 5 divided by 3. That's the side adjacent over the hypotenuse. So that takes care of cosine, and tangent will be negative, and that's the opposite over the adjacent. And the only thing that would be expected in this problem is for you to rationalize the denominator. So this becomes tangent of theta equals -2 times the square root of 5 over 5. And those are the two answers. And problem number 9. Find the exact values. All right, the exact value. And there's two parts to it. A is the sine of -5 pi over 6. So let's see what we're dealing with here. First, let's change from radian measure to degree measure. So let's make the sine of whatever 5 pi over 6 into 5 times 180 over 6. And 6 into 6 is 1. 6 into 180 is 3. And not 3, but 30. So this is really the sine of negative 150. All right, and it's a negative. So, somebody pulled a fast one on us. No problem. We're going in the negative direction. Not a problem, right? Not a problem. -270, -360. Here's where the angle will be going in the negative direction. So the terminal line, since it's in negative, it's negative. A negative angle. The angle is going to be negative. This is going to wind up in the third quadrant. But let's convert it to a positive angle. And if it's -150,
then going in the positive direction, it will be 360 minus 150 is 210, which definitely makes sense. That's an angle between, now we're going in the positive direction. So, you know, you kind of have to think of this as not only negative 270 going this way, but going the other way, it's going to be 90, 180, and then 270, right? So it's kind of weird, a problem like this. But but the bottom line is we're looking at the sine of 210 degrees, okay? And that will be equal to, now when you're converting an angle, it'll be 210 minus 180 is 30. So we're looking at the sine of 30 as the reference angle, but it's in the third quadrant where it's going to be negative. And the sine of 30 is a half, so that's negative a half. So in other words, the sine of negative 5 pi over 6 is equal to negative 1/2, I think. Yes, got it right. So basically what you're doing is when you have, you're converting from radian measure to degree measure, and then you're subtracting whatever you get if it's negative from 360, and that'll give you the positive angle of 210. So we're really talking about the sine of 210. But in the third quadrant, to change an angle of 210 to a reference angle, that's an angle between 0 and 90, we have to take 210 and subtract 180. And that's where the 30 comes from. And this is going to be the sine of negative the sine of 30, because it winds up in the third quadrant. And that's going to be negative 1/2. And that's the end of the problem. Okay, and then we have, as part B, arc cosine of the square root of 3 over 2. So first, the reference angle. The reference angle. So actually, before we do that, let's discuss the restricted domain. The restricted domain, like what do we have? What angles are we talking about? And the restricted domain for cosine is 0 to 180. People got this wrong on the test because they say, negative 90 to 90. But for cosine, it's different. It's 0 to 180. Tangent and sine are negative 90 to 90. But in terms of finding an inverse function of a trigonometric function, then it's 0 to 180 is the restricted domain for cosine. Okay, so when is the cosine equal to the square root of 3 over 2? The answer is that the reference angle will be 30 degrees. And it's positive. So it's going to be here, and then the cosine is negative in this quadrant, so it can't be that, and the answer will be 30 degrees is the angle. And that's how you do that problem. So problem number 10. Problem number 10 wants us to verify a trigonometric identity. So tangent of x plus cotangent of x is equal to secant of x plus cosecant of x. So this is interesting because every single thing in this problem requires a substitution. Tangent is sine over cosine. Cotangent is cosine over sine. Secant is 1 over cosine. And cosecant is 1 over sine.
Okay, so, let's work with this. Let's work with this and let's get, since we're adding two fractions, we're going to need a least common denominator. So the least common denominator is going to be sine x cosine x. Sine x cosine x. So to get from here to here, we're missing a sign. To get from this denominator to this denominator, we're missing the sign. So we put in the sign. And that'll give us sine x, sine squared x. Here, to get from the old denominator to the new denominator, you're missing the cosine. So we need to multiply by cosine over cosine. And that will give us cosine times cosine is cosine squared. And that will be equal, and let's just leave it like this. Let's leave it like this and see what happens. I mean, we may have to combine the two fractions. I don't know, but let's just see what we could get over here. Yeah, I think we're going to all right, well, if we add them, we get sine squared plus cosine squared over sine x cosine x, right? And this will equal 1. So 1 over sine x cosine x equals, oh, there's got to be an easier way. Something is definitely wrong. What is wrong with this problem? What is wrong with
Oh, the
this?
second part is multiplication.
I just looked again at the problem. Yes, that makes a very big difference, doesn't it? Yes, I just realized that, but thank you. But I just looked back at the problem, and yes, indeed. So this is multiplication, which means that these two are being multiplied. And there it is. That's the end of the problem. That's what was missing. That was the missing link. The missing link was that that's multiplication, which would make, this equal to this. And that's all we needed to do. So there it is. That's the whole problem. So the only thing, first you needed to make all the substitutions. Then you needed to combine the two fractions. And you wound up with the Pythagorean identity in the numerator, which you made into 1, and then the sine cosine, and that's exactly what you had on the right side. So problem number 11. Given the polynomial h of x equals 3x to the third minus 2x to the second minus 11x plus 10. All right, so this is actually considerably more difficult than the problem we had yesterday because of that 3. That 3. So we take all the factors of 10, so plus or minus 10 divided by plus or, and then, so in other words, when we look for the possible, list all possible rational zeros, it'll be the factors of 10 divided by the factors of 3, plus or minus. So it's going to be positive 10 plus or minus 10 divided by plus or minus 1, and plus or minus 10 divided by plus or minus 3. Then plus or minus 5 divided by plus or minus 1, and plus or minus 5 divided by plus or minus 3, and then plus or minus 2 divided by plus or minus 1, and then plus or minus 2 divided by plus or minus 1, and then plus or minus 1
divided by plus or minus one. This takes care of part A, which is to list all possible rational zeros. But we know basically that what we're looking for is, well, they're giving us a very important piece of information. Forget about what I was just about to say. List, so using either long division or synthetic division, show that -2 is a zero. So they're telling us that -2 is indeed one of the zeros, but prove it, prove that that's true. So you take, I'm using synthetic division, as I always do. 3, -2, -11, and 10. The -2 on the outside. Bring down the 3. -6, -8, +16, +5, -10. There it is. Drops out. That's it. So this is one of the zeros. We could put it up here. X equals -2 is one of the zeros. Okay. Now, here's the rub right over here. Now, I would say that on a final exam, from my experience, when you suppress the equation to look like this, that this will be factorable. So it's not like you're going to have to use the quadratic formula and come out with something, because they're asking for the linear factorization. Usually when they ask for that, it means that all of the zeros are going to be rational zeros. So this could be factored. That's what I'm trying to say. This could be factored. And the factors, that's it, right? So -5 times -1 is +5, and then -5 and -3 is -8. So that works out good. Now you set each factor equal to 0. X equals 1. Well, a little more work here, right? 3x equals 5, and x equals 5/3. Okay, so in other words, x equals -2 is one of the zeros. Another zero will be x equals 1, and the last zero will be x equals 5/3. So these are the zeros of this original polynomial. Okay, now the linear factorization, remember what I said, is simply the opposite of this. So x plus 2 times x minus 1 times x minus 5/3. In other words, this would be it. X plus 2, x minus 1, x minus 5/3 equals 0. That's the linear factorization. The only thing that I might suggest that you do to make it look nicer and to impress your next professor, if this comes up, is take this 3, put it with that x, and make it look like that. Because, and there's a reason, we're not just playing games. You're actually combining the two fractions, and you're getting 3x minus 5 all/3. But since it's equal to 0, you can, if you cross multiply the zeros, the 3's drop out. So you just wind up with the 5x. And this is the answer. This is the linear factorization. Here are the zeros. And that's the whole problem. Not a difficult problem, because on my test, if you remember, I said to you, here's a polynomial, find all the zeros. Here, they're telling you that one of the zeros is -2. Just show that it's true. So that's great. You don't have to say, well, is +10, -10. You don't have to go through any of this stuff that we went through when we were doing it. Yeah, if you look back at that second test, because this is chapter 2. If you went back to that second test, you'll see that the problem was much more difficult in many ways. Here they're giving you an answer, and all they're asking you for is to prove it. And then you get this equation, which is going to be factorable. And, the rest of it just flows. It's very, very nice. And that's what'll be on your final exam next Monday. Same kind of problem, where you're given one of the zeros. That's always a very, very tremendous benefit. And problem number 12, do we have room? I say yes. I say that we do have room. Okay, so you're given the following function. Let me drop this down. You're given the following function. I'm putting an exponent of 1 up there. And, you're not really supposed to do that, but I'm doing it anyway. Because, we'll be using the fact that the multiplicity is 1. And you know how I do this problem? I create a chart. I would appreciate it if when you did this problem on an exam, like the final, for example, that you also use a chart, because it makes it easier for me to figure out, what you're saying. People have it all, make it as easy. I keep saying this because it's just very, very important that when you do these problems, you make it as easy as possible for me to grade it. So here we have 2x to the third, x minus 3 to the first, x plus 1 to the second. Those are the factors. Here are the zeros, or the roots. You can call it anything you want. This is 0. Whenever it's just something like this, it's equal to 0. This is equal to 3. X is equal to 3. And x is equal to -1. The multiplicity. And remember that multiplicity simply means the exponent. So 3, 1, and 2. Then I like to say, odd or even. It's easy. 3 is an odd number. 1 is an odd number. 2 is an even number. And then, does it go through the x-axis, or does it bounce on the axis? So if it's odd, it goes through, and this is a bounce. Okay, now what we'd like to know, and what's actually asked for, is the degree of the polynomial, the degree of g of x, which is simply going to be the sum of the multiplicity. So 3 and 1 is 4, and 2 is 6. The end behavior kind of, they want you, I want you to draw this. So this is what
the end behavior when it's an even number. When that degree of the polynomial is an even number, then this is what the end behavior will look like. So whatever we draw, we know it's going to start here, do all kinds of things, and then wind up over there. Okay, so let's graph it. Now we graph it. And the roots are 0, 3, about over there, right? And -1, let's say over there. All right, so here's the graph. The graph is coming down this way. And when it gets to -1, wow, it gets to -1 first, and it bounces. So it gets here, and it bounces. And then it has to come around because the next root is 0, and that's right next to -1, so it's not going to go very high. It's going to come down like this, and it's going to go through at 0, and then it's going to go probably, I think it's going to go very, very low, because there's a lot of room here, and it usually goes like very, very low, comes back up to 3, where it will again go through, which makes a lot of sense, because that's what the end behavior tells us. It's going to start in the second quadrant, end up in the first quadrant, and there it is, doing the same exact thing it's supposed to. Again, I don't need to know how far down it goes or what this is. That's all I need to know. And that's the end of the question, and indeed the end of that particular final exam that was given last fall.